Thank you, everyone. In March of this year, attackers compromised a number of trusted software supply chains. These included Trivy, Light LLM, and Kix. The malicious code that they deployed didn't need to battle through firewalls, didn't need to exploit 0 days to actually get into customer environments. Those customers actually invited the code in of their own volition. Now, the attackers behind this particular attack I'm talking about were after something really valuable. They were after access in the form of identities, tokens, and credentials, all the sorts of entities that can be accessed by trusted software. Now imagine that attack was carried out by a single AI agent. So we know that AI agents are very versatile. They can read documentation, they can write code, they can manipulate cloud infrastructure. And they can do all of these things without needing to seek approval from humans. Now, the reverse flip side of that coin is that many organizations are deploying the same AI agents to perform legitimate tasks. And they're doing this by providing increasing amounts of autonomy to these agents. So the question we need to ask ourselves is, these agents, what happens if one of them is compromised or manipulated? What happens if it just makes a bad decision? But actually, what happens if someone else's agent is crawling all over our network? So what I want to do in the next few minutes is to explore what we can learn about securing AI workloads, AI agentic workloads, learning from software supply chain attacks. So have I gone the wrong way? Oh, I haven't. Let's consider the threat landscape. So agentic powered cyber attacks haven't been around that long. They were starting to be reported by analysts as recently as 2024. But their use has grown rapidly. Any software is fair game for these exploits. So vulnerabilities that have been hidden from humans for many years are now being uncovered by AI as a matter of course. Furthermore, that the skills that are required to deliver these complex cyber attacks is shifting. No longer is it necessary to have deep technical skills. What you actually need is the ability to provide the right prompts to AI agents and AI systems. And here's the thing, AI agents are relentless. They don't eat or sleep. They operate 24/7. They don't actually need 24/7. They're operating at machine speed. They can assess every facet of a system, and they can probe for and look for vulnerabilities in a way that humans simply can't. So we now find ourselves in an arms race between AI exploits and our ability to defend. And there's good reason why agentic AI has become prominent in cyber attacks. Automation means that cyber criminals can be more productive and they can actually perform more attacks. They can do more for less. Orchestration of complex cyber attacks is difficult. It takes time. But now it can be done very quickly and much more effectively. Adaptability is key to the success of cyber attacks, so the ability to evade security and also deal with the unpredictability of these complex attacks is important. And all of this complex and highly adaptable capability is available through AI agents, operating at machine speed without any need for human intervention. So I'm just going to go through an example of a complex software supply chain cyber attack, one that I alluded to a couple of minutes ago. This attack was a significant attack and was actually compressed into a matter of a few days in terms of execution, and it happened back in March of this year. There's quite a lot of detail in the slides that follow. They in themselves only scratch the surface of the attack itself. What I'll try and do is paint a picture of how the attack unfolded. The attack was performed by a group called Team PCP. This is a financially motivated cyber criminal gang which specializes in software supply chain attacks, and it targets cloud infrastructure and developer environments. The choice of Trivy was very deliberate. Trivy is a security scanner, and as such scanners require wide system access in order to examine code bases for vulnerabilities. So the first phase of the attack was to establish a beachhead. An AI agent called hackerbot-claw searched through GitHub for vulnerabilities and found one which revealed a privileged access token. This was quickly weaponized by the attackers, or should I say by the AI agent, and it used this particular token to overwrite release tags for software. This enabled the insertion of malicious code through Trivy distributions via GitHub. This code was designed to find and harvest accesses, permissions, credentials, etc., and to copy those into a hidden repository, which then could be accessed by the attackers at a later date. The agent also covered its tracks by deleting all evidence of his activity within GitHub, so it made this attack really hard to uncover. The attack then extended. It extended to a company called Checkmarx, a cybersecurity company, and specifically one of its products, Kix. Kix is also a security scanner, but in this case, it focuses on infrastructure as code. So the attackers moved to a different part of the technology stack. It reused tokens from the first attack, and once again, it overrode release tags to enable itself to insert the same malicious code with the same intention into the Kix distributions. Whilst this was happening, the original attack on Trivy was extended to insert, again, the same malicious code into the Docker container distributions for Trivy. The attack didn't stop there. The attackers, or rather the agentic AI agent, created another software distribution channel for its malware, this time targeting Light LLM. Light LLM used Trivy as a security scanner, so the AI agent used that compromised version of the scanner to look for exploits and managed to expose the PyPI publishing token. It then used that token to put the same malicious code into the Python packages that are distributed by Light LLM. So what's the takeaway from this attack, this complex attack? It was a sophisticated supply chain attack. So planning these complex campaigns, the cyber attack chains, takes a lot of effort and is very difficult to do and would ordinarily take months. This was done in a matter of weeks, and the execution happened within a matter of a few days, a couple of weeks. The attackers targeted well using a security scanner as the distribution channel for its malware, and also the agentic AI provided it with the ability to find vulnerabilities as required to ensure that the momentum of the attack was maintained. And all of this was orchestrated by an AI agent. So, how can we defend against this? Because this is scary stuff. Basically, what we need to do is to build engineering trust within our organizations, and I'll get into what I mean by that in the next few slides. This is important for two reasons. One is defending against cyber attacks that use agents in the way that I've described, but actually it's exactly the same for us when we try and safeguard our own agentic AI workloads within our organizations, using the same approaches, the same principles, and the same techniques. What that does is to ensure that if any of our workloads go rogue, they do not deliver the same outcome as the cyber attack that I've just described. So just looking at specifically the Light LLM exploit, so have you seen the key element of this attack was the insertion of malicious code into trusted software products that then would be able to access sensitive information, in this case, access equities, within customer environments. So there are things that you can do, and the list I'm going to go through in the next couple of minutes or so is not exhaustive. Sort of looking left to right, you can use lock dependencies. So for those packages that you regularly download, using tools that attach a unique hash, like a SHA-256 hash, to those packages, so that if the package contents change without warning, there is a hash mismatch, which would then allow you to abort the installation automatically. Moving to runtime, validating execution, and there are lots of ways of doing this. One of the techniques, for example, is parent-child tracking. So understanding those patterns within your organization so that any unauthorized or rogue child processes can be blocked before they get going. And network segregation and controlling network egress. These are things that have been around for many, many years, but still not always done very well. These are important, and you can do this, and increasingly you can do this through network configuration. but also with the use of hardened gateways between network segments and also at your boundary. So this serves to do two things. One is to restrict the blast radius to a network segment should there be a compromise, but also it serves to stop the exfiltration of valuable equities from your organization to the attackers outside your boundaries. I've said that adaptability is hugely important for the success of complex cyber attacks and supply attack chains across multiple organizations. And the rise of polymorphic malware is hugely important in delivering successful attacks. Things like rewriting code on the fly, AI in the loop, so that you can dynamically change the prompts that you provide to your agents or to other AI systems within your targets. All these things cannot really be detected by static signature-based defenses that we've used in the past. But there are things that you can do to mitigate the risk. So the deployment of monitoring tools that are configured for behavior heuristics, so that using patterns developed in your organization, but also across numerous organizations, can be used to try and spot anomalous behaviors that could indicate malicious intent. AI providers deliver services that you can use to monitor the misuse of AI tokens, and again, using patterns looking for suspicious prompts. And again, a return to network segregation and controlling the egress of data across your network boundary. In this case, this is really important in ensuring that attackers outside of your organization cannot communicate and direct the agents. Just a few more things on some of the controls that you can put in place. So keyless authentication and just-in-time access are really foundational implementation patterns for zero trust. They support the concept of continuous identity verification, time-bound access, and the principles of least privilege or minimum access. So for example, just-in-time access is really important where you've got privileged user accounts, where you make sure that those accounts are only active when they're absolutely needed, and for the bulk of the time they lie dormant or effectively revoked, so they're not available for attackers to use. These are all assuming that credentials can be stolen and probably will be stolen at some point, and make sure they limit the use of those credentials. Staying on the subject of credentials, the other thing that you can do is to ensure that the credentials on their own are actually insufficient. So deploying approaches like contextual access controls, where access requests can be validated against a set of multiple policies, which could look at things like authorization scope, network context, geographic location. Failure of any of those checks could result in the request being denied, or it could result in targeted human intervention at that point. This ensures that you prevent misuse of those credentials even when valid ones are presented. I've talked about data exfiltration, I've talked about network segregation, which has been around for a long, long time. But in modern architecture, certainly within cloud, you can set perimeters around entities such as APIs and around data and services. And these are really important. An example are API gateways. So these gateways can enforce security controls and request validation when API calls are made, such that if there are any unexpected API calls or anomalous API calls, these can either be blocked or, once again, targeted human intervention can be initiated. So my final point is about human interventions. There is a lot of talk, and I include myself in this, where people talk fairly glibly about human in the loop, as if it's some sort of silver bullet or panacea in terms of securing AI workloads and certainly agentic workloads. Now, it's vitally important that humans are governors of AI-based systems, but it's totally unrealistic for humans to be monitoring and supervising all the tasks that are undertaken by AI systems. You just lose the benefit of the AI system in the first place. So therefore, it's important to set safeguards and boundaries for agentic workloads using some of the techniques I've talked about. And within those boundaries, it's really important that you have targeted human intervention only when needed. There's a term that's become popular that I really like that refers to cognitive speed bumps. These are deliberate mechanisms that you can use to slow down, consider, and obtain approval for consequential actions before they're actually taken by AI agents. Examples could be if an agent wants to delete a backup, or if it wants to create a new privileged user account or stand up some cloud infrastructure. At that point, you can then bring in some targeted human intervention. So just as a physical speed bump slows down a car, a cognitive speed bump can slow down a consequential decision. Thank you.